right? D block elements. What are D block elements? This is the definition. Elements belong to group number 3 to group number 12. Okay, in the periodic table are called D block elements. Okay, from group number 3 to group number 12 in the periodic table we have some elements, and those elements are called as D block elements. Okay, so in group number 3 we have elements. I'll write in this manner, therefore it will be easy for you. Actually, in the periodic table, D block elements, right, starts from fourth period. First period, you know very well, the first period elements, hydrogen and helium occupy the first period. Then second period starts from lithium and ends with neon. Third period starts with sodium and ends with argon. Okay. Then in the fourth period, right, we have the D block elements. So D block elements, right, starts to appear in the fourth period of the periodic table. So fourth period, right. The list of D block elements present in the fourth period is actually called as 3D series elements. Why 3D series? We'll discuss. 3D series. So what are the elements present in 3D series? The elements are scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper and zinc. Okay, these are the elements present in the 3D series, right? We call this series of elements as 3D series, right? Students, for your level, it is very important to remember the 3D series element. 3D series elements are also called as first transition series elements. Okay, let me write here. 3D series is also called as first transition series. First transition series or first transition elements. Okay, so remember this information, very very important. And these are the elements present in the fourth period of the periodic table. They are called as 3D series elements: scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper and zinc. Then in the fifth period we have 4D series elements right here. So we have 4D series elements present in the fifth period of the period table, also called second transition series. Right here we have the element starts from yttrium and ends with cadmium. Yttrium to cadmium. What are the elements? Below titanium we have zirconium. Below vanadium we have niobium. Below chromium we have molybdenum. Below manganese we have technetium. Below iron we have ruthenium. Below cobalt we have rhodium. Below nickel we have palladium. Below copper we have silver. These are the elements present in the 4D series of the periodic table: yttrium, zirconium, niobium, molybdenum, technetium, ruthenium, rhodium, palladium, silver, cadmium. This is also called second transition series. These elements are also called as second transition series elements. Second transition series are usually called as 4D series. Clear? Then another series we have, actually we have two more series, but the 5D, 3D, 4D, 5D series are very famous. These elements are very famous. So I am not going to discuss 6D series here. So the next one is 5D series. 5D series. 3D, 4D, 5D series element, also called third transition series. Okay, what are the elements present here? The elements are scandium, yttrium, then it starts from lanthanum, okay, then titanium, zirconium, below zirconium we have hafnium, vanadium, niobium, tantalum, chromium, molybdenum, tungsten, manganese, technetium, rhenium, iron, ruthenium, osmium, cobalt, rhodium, iridium, nickel, palladium, platinum, copper, silver, gold, zinc, cadmium, then we have mercury. Okay, these are the elements present in the 5D series. Okay, 3D series belong to 4th period in the periodic table, 4D series belong to 5th period, and 5D series belong to 6th period of the periodic table. Okay, generally we discuss these elements under D block. Okay, we also have another series which is incomplete. We are not going to discuss that. Okay, in general, if people ask D block, okay, we normally discuss these elements. Okay, these are the elements present in D block. Okay, what are D block elements? Very simple. Elements belong to group number 3 to 12. From group number 3 up to group number 12, these elements are called as D block elements.
Yes, sir.
Okay, I'll proceed further. Then next important point is that what are transition elements? Transition element, the old definition is this: elements present in between S block and P block. You know very well, in the periodic table we have 4 blocks of elements. You might be knowing this. We have 4 blocks. This is S block, and we have P block here, and we have a separate block at the bottom of the periodic table. Listen, student, this is actually S block. Group 1, group 2 elements are called S block elements. From group 13 to group 18, these elements are called as P block. Okay, from elements belong to group number 13 to group number 18. These elements are P block, and these elements present from group 1 and group 2 are S block. In between we have elements from group 3 to 12. These elements are called as D block. So D block elements are present in between S and P. You know very well, S block elements are S block elements are having high metallic character, whereas P block element, most of the P block elements are non-metals. So when you move from left to right, okay, what happens? Metallic character, right, decreases and becomes non-metallic when you move from left to right. Clear? So since these elements are in between metallic and non-metallic, we call them as, in those days, people called these elements as transition elements. This is the old definition. Transition elements means elements present in between S block and P block. But what is the modern definition? The modern definition is, this is the definition you should give in the examination. What is the definition? Definition is this: elements having incompletely filled d orbital, d subshell. Elements having incompletely filled d subshell in the neutral state or in any of the common oxidation state. Students, observe carefully. You take any element and see their configuration. See the configuration. If the d subshell is incompletely filled, you know very well, a d subshell can accommodate maximum of 10 electrons. maximum of 10 electron. A d subshell can accommodate maximum of 10 electron. If you have electron less than 10, then we say that it is incompletely filled. Students, observe carefully. So from electron 1 to electron 9, up to 9, from electron 1 to up to 9, we say that it is incompletely filled. Incomplete. Clear? 10 means complete. Up to 9 it is incomplete. So elements having incompletely filled d subshell in neutral state, the atom may be neutral atom, or in any of the common oxidation state. Okay, any of their common oxidation state. Some elements may exist in +1 state, some element exists in +2 state or +3 state. Okay, if any of these in this common oxidation state, if element has incompletely filled d subshell, then we call them as d block elements. Transition elements. Okay, this is the definition for transition element. Now listen, student, here we have few questions to ask. See here. So in the periodic table, I have told you we have these elements, and see group number 12, the elements which are present in group number 12. In group number 12 we have zinc, cadmium and mercury. You know very well, out of all these elements, mercury is the only liquid element, liquid metal, if you ask me, I say like that. Mercury is the only liquid metal, okay, present in D block. Right, so now I am focusing on group number 12. We have zinc, cadmium and mercury. If you see their electronic configuration, I am going to discuss that electronic configuration in the next part, okay, of this lecture. But before going to see that, let me give this point here. The electronic configuration of zinc is 3d10 4s2. Students, observe carefully. 3d10 4s2. Here d subshell is completely filled. Now take the common oxidation state of zinc. The common oxidation state of zinc is zinc 2+. Zinc in 2+ state. Zinc 2+ means you should remove 2 electron from S. So if you remove electron here, remain the 3D, again the 3D subshell is fully filled. So in the neutral state or in the common oxidation state, okay, D subshell is fully filled. Here as well as here, D subshell is fully filled. Therefore zinc is not a transition element. Is not a transition element, students, as per definition. Is not a transition element. Keep this point in mind, very important. Now I'll take the second element, that is cadmium of group number. These are all elements belong to group number 12 in the periodic table. Cadmium, the electronic configuration is 4d10 5s2. Okay, again see D subshell is fully filled. Now the common oxidation state of cadmium is also 2+. Cadmium 2+, 2+ means remove 2 electron from the s orbital or s subshell. You'll get 4d10. Again see, this is completely filled. So cadmium in the neutral state or in the common oxidation state, in both these states, the D subshell is completely filled. Therefore cadmium is also not a transition element. Then if you come to mercury, the electronic configuration is 5d10 6s2. Mercury exists in two different oxidation states, Hg+1, Hg+2. This is mercurous and this is called mercuric. Hg+1 is called mercurous. We say that it is mercurous ion. Hg+2 is called mercuric ion. Mercuric. Clear? +1 means from neutral state you remove 1 electron. You remove 1 electron from S, you will get 5d10 6s1. See, even in this oxidation state, D subshell is fully filled. Hg2+ means from mercury you remove 2 electron from S, you will get 5d10, that is also fully filled. So now listen, student, zinc, cadmium, mercury, these elements belong to group number 12. right, in all these elements, right, in the neutral state or in their common oxidation state, D subshell is fully filled. Therefore, these elements are not considered as transition elements. They are D block elements because they belong to group number 12. So they are D block element, but they are not transition elements. Is this point clear, student? So group number 12, we have these elements zinc, cadmium, mercury, and these elements in the neutral state or in their common oxidation state, they have fully filled D subshell. Since D subshell is fully filled, these elements are not considered as transition element. They are not transition elements. They are just D block elements. So this is a very important point you should keep in mind. All transition elements are D block elements. But the reverse is not true. That is, all D block elements are not transition elements. See, group number 12 elements, these are exceptions. They are just D block element, but they are not transition elements. So keep this point in mind. All transition elements are D block elements, but the reverse is not true. That means all D block elements are not transition elements. Okay? Is this clear, student? Now, let me ask a few questions here, student. Try to answer this question. Is copper a transition element? Copper, the electronic configuration of copper is 3d10 4s1. This is the electronic configuration of copper. Copper exists in two common oxidation state. The common oxidation state is actually it exists in +1 state as well as +2 state. +1 means we should remove 1 electron, so we'll get 3d10. +2 means we should remove 2 electron from neutral atom, you'll get 3d9. Yeah, students, can you tell me, is copper a transition element?
Yes, sir.
Yes.
Yes, sir.
Yeah, because in one of the common oxidation state, there is copper 2 plus, copper +1 is cuprous. Copper +2 is called cupric. Okay. In one of the common oxidation state, the D subshell is incompletely filled. Therefore, copper is a transition element as well as D block element, because I told you all transition elements must be D block. Okay. Similarly, silver, gold, right? Silver and gold, they are all transition elements. Keep this point in mind, very, very important. Okay. Then, now we'll see another important part of this D block element called electronic configuration. Okay. Electronic configuration means how electrons are arranged in different subshells of an atom of D block, of the atom of D block elements. Okay. Now, the general outer electronic configuration for D block is n-1 D 1 to 10 ns 1 to 2. This is the general outer electronic configuration of D block elements. n-1 D 1 to 10 ns 1 to 2. Students, keep this point in mind, very, very important. This is the general outer electronic configuration of D block element. Okay. Now, in the periodic table, except palladium, there is an exception. Except palladium, all other elements have some electrons in D subshell, some electron in S subshell. But in palladium, right, we have electronic configuration 4d10 5s0. This is one important exception. There is no electron in the S subshell. Okay, palladium is an exception, note down. In all other D block elements, if you see, we have some number of electron in d subshell, some number of electron in s subshell. Okay, then now listen students, this is very important for your level to remember the electronic configuration of first transition series, also called 3D series. Other series is important if you prepare any competitive examination. Okay, but for your for your general examination or board examination, 3D series is sufficient. So 3D series. In 3D series, we have elements like scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper and zinc. These are the elements present in 3D series. What is the outer electronic configuration? First, I'll give their atomic number. Atomic number starts from 21, student. 21 for scandium, 22 for titanium, 23 for vanadium, 24 for chromium, then 25 manganese, 26 iron, 27 cobalt, 28 nickel, 29 copper, 30 zinc. These are the atomic numbers. If you remember atomic number, it is easy to write the electronic configuration. How? See, for scandium, the electronic configuration, outer electronic, since they are all 3D series, 3D subshell is incompletely filled. Okay, in 3D series element, 3D subshell, right, is incompletely filled or completely filled, because I am talking about D block. So for scandium, the electronic configuration is 3D. Students, observe carefully. 3D, put 4s. 3D 4s. Observe carefully, student. Here we have 21. No, put 1 here and 2 here. 3D1 4s2 is the electronic configuration, outer electronic configuration of scandium. Then what about titanium? I'll write in the upper side. Titanium atomic number is 22, 22, right? 22. So I'll write 3D 4s. In both the place you put 22. Then vanadium I'll write down. 23 is there. So 3D 4s. Put 3 here and 2 here. Remember this. Second number you place it on D. Clear? Then I'll go to manganese. Students, observe carefully. Manganese. Chromium I'll write later, because chromium and copper, these two elements are exceptions in 3D series. So I'll write later. Manganese 25 is the atomic number, so electronic configuration is 3D5 4s2. Right? Iron 3D6 4s2. Iron. Cobalt 3D7 4s2. Cobalt. Okay, then nickel 3D8 4s2. Up to this there is no problem. Copper is an exception, we'll discuss that. Zinc 30, the electronic configuration is 3D10 4s2. Okay, student, it's very easy, no? If you remember the atomic number, you can easily write the electronic configuration. So first remember the elements. You should remember the elements in the same order. Okay, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. Remember in this order and write the atomic number from 21, 22, 23, okay, like that. Then you can write the electronic configuration from the atomic number itself. Directly you can write. Now listen, student. I have told you that chromium and copper, these two are exceptions. Why? To get the extra stability, their electronic configuration is slightly modified. Okay, the modified electronic configuration I'll write for chromium. It is 3D4s. What is expected? Expected is 3D4 4s2 expected. But to attain extra stability, right? D subshell become 5 and S subshell become 1. You know very well, D subshell with 5 electron is half filled. S subshell with one electron is half filled. Now both the subshells are half filled, so the stability is very high. You know very well. Fully filled subshell, half filled subshells are more stable due to symmetry. Okay, or due to exchange of electrons, we can say the other way. Right? Remember, student? Chromium electronic configuration is 3d5 4s1. In a similar manner, for copper, the expected configuration is 3d9 4s2 expected. But to get the extra stability, the configuration becomes 3d10 4s1. So in the first transition series, chromium and copper, okay, are the two exceptional elements having different configuration. Take note, student. Chromium and copper. So these are the electronic configurations of the 3D series. I am not going to discuss 4D and 5D here. Okay, 4D and 5D, yes, similar exceptions are there in 4D and 5D also. Okay, for your level, at least remember the 3D series. Okay, this is very important. Is this clear, student? Any doubt?
No doubt, sir.
Yeah, good. Now, with this in mind, half-filled subshell, and fully filled subshells. Okay, they are more stable. Okay, if the subshell is half filled or fully filled, it is highly stable. For S subshell, okay, if S subshell has one electron, it is half filled. If S subshell 2 electron, it is fully filled. So both these are stable configuration for S subshell. For P subshell, P3 is the off filled, P6 is fully filled. For D subshell, D5 is half filled, D10 is fully filled. Both these are generally stable configurations. Subshell with the half filled configuration, subshell with the fully filled configurations are generally stable. Similarly, for F subshell, F7 and F14, half filled, fully filled, they are generally stable. Clear? Students, keep this point in mind, very important, student. Now, we'll discuss about physical properties of these elements, D block elements. Okay, so take down physical properties of D block elements. Let me take the first physical property, that is size of atoms. Okay, so one second. Right. So we are going to discuss about the physical properties of the D block elements. Physical property means size, how size varies from left to right, from top to bottom, okay, and how ionization enthalpy changes, how melting point changes, okay, how boiling point changes, how enthalpy of vaporization changes, right? If you discuss all these, okay, all these properties comes under physical properties. Okay, we are going to discuss chemical properties separately. Clear? Now, in the physical property, the first property that we are going to discuss is size of the D block elements. Size means you can say size, or you can compare size by making use of their atomic radii. Okay, you can compare the size of ions by making use of their ionic radii. For neutral atom, we take atomic radius. For ions, we take ionic radius. Okay, in plural, we write radii. Okay, now how size of the atom, first I'll take atom, then we'll discuss ions. How size of the atom varies. Okay, how size of the atom varies, right, in D block. Okay, students, observe carefully. In general, if you compare D block element with S and P block, okay, when you move from left to right in the periodic table, listen, in general student, in general, when you move from left to right, when you move from left to right in the periodic table, what will happen? Effective nuclear charge increases. In general, effective nuclear charge increases from left to right. Therefore, in general, size decreases. From left to right. From left to right, size decreases. So if you compare the size of S block, D block and P block, S block elements are larger in size compared to D. D block elements are little larger in size compared to P. So this is the size order of S block, D block and P block elements. Okay, so size of D block element is in between S and P. Actually, S block elements are larger in size. Clear? Then next point. Okay, to understand size of D block element, these two quantities are very, very important. One is effective nuclear charge, the other one is screening constant, also called screening effect. We represent this by the symbol sigma in general. What is effective nuclear charge? Listen student, effective nuclear charge is measured based on how the nucleus of an atom attract the electron present in the valence. Suppose, assume that this is a valence shell and we have an electron here. How this electron is attracted by the nucleus. Okay, so the effective nuclear charge is measured based on this attractive force. When you move from one atom to another atom from left to right, students observe carefully. When you move from left to right in the periodic table, or in D block very specifically, in D block, when you move from left to right in D block, effective nuclear charge increases. Because when you move from one element to the next element from left to right, what will happen? One proton is increasing in the nucleus. One proton is increasing. Neutron also changing. That is not important now. I am talking about only proton. When you move from one element to the next element from left to right in D block, okay, a proton is increasing. Therefore, positive charge on the nucleus increases. So effective nuclear charge is very high. Because of that, okay, the attraction increases. So when you move from left to right in D block, effective nuclear charge in general increases. Keep this point in mind, very, very important. Then the next one is, what is meant by screening? Screening effect. What is the meaning of screening effect? You know very well, in atom you will be having nucleus and there are many inner shells and we have an outer shell called valence shell. Suppose I have an electron here. Okay, nucleus try to pull that electron towards it. Okay, because this is negative, electrons are negatively charged, nucleus is positive, so nucleus try to pull the electron towards itself. But if you have electron in between, if you have electrons in the inner shells, what these electron will do? These electron will screen the outer electron from the nuclear attraction. Students observe carefully. When you move from left to right, okay, in D block, especially from one element to the next element, not only number of proton increases in the nucleus, electron also increasing. And very specifically, electron is increasing in the inner D subshell. Okay, when you put electron in the inner D subshell, what will happen? Screening also increases. So when you move from left to right, students observe carefully, screening effect sigma also increases from left to right. Screening effect also increases. So size, actually, if effective nuclear charge increases, size will decrease. Size is inversely proportional to effective nuclear charge. If effective nuclear charge increases, size will decrease. Whereas screening effect and size, their size is directly proportional to screening effect. If screening effect increases, size increases. Students, both these are very important points. Keep this in mind. Okay, now what happens in the case of D block, very specifically 3D series. In 3D series, students observe carefully. In 3D series, when we move from left to right, scandium to titanium, yes, size decreases. Titanium to vanadium, size decreases. Vanadium to chromium, size decreases. Up to this, size decreases. Why? The reason is effective nuclear charge increases compared to increase in shielding constant or shielding effect. So effective nuclear charge is more, right, up to this, effective nuclear charge is more compared to shielding. That is the reason why, since effective nuclear charge is increasing in a larger extent, if effective nuclear charge increases, size decreases. So size decreases from scandium to chromium. Okay, this is the size order. Size decreases up to chromium. Then after chromium, suddenly, students observe carefully, suddenly for manganese, size become large. Size increases. Even compared to iron, size of manganese is large. Okay, this is a very important one. This is what experimentally observed. Okay, experiment tells that this atom has little higher mass compared to chromium, iron and the nearby elements. What is the reason? The reason is the metallic structure. You know very well, all metals, students, except liquid metals, all other solid metals have definite crystal structure. Due to the typical crystal structure, okay, the size of manganese atom is little larger. We measure radius, okay, in crystal arrangement. Okay, in the crystal structure, the manganese atom distance is somewhat large. Okay, so since the two atoms exist in larger distance, right, the radius increases. Okay, so keep this point in mind. It's very, very important, student. This is experimentally observed. Then after this, what will happen? Size of iron, cobalt, nickel, they are almost the same. Size of iron, cobalt, nickel are almost the same. What is the reason? Why size almost the same for these elements? The reason is the increase in effective nuclear charge and the increase in screening constant, they are roughly equal. Okay, increase in effective nuclear charge, increase in shielding constant, both are equal. Okay, effective nuclear charge and screening constant for all these elements are equal. Therefore, the size of these atoms remains same, almost same. After nickel, what will happen? There is an increase in size, student. Size increases. So compared to nickel, size of copper is large. Compared to copper, size of zinc is large. What is the reason? The reason is here effective nuclear charge in these two elements, effective nuclear charge, and if you compare with the screening is large for these elements. Since screening is large, size increases. Okay, Tech 2 students, very important. For 3D series, you should remember the variation, how size varies. From scandium to chromium, size decreases. Suddenly for manganese it increases. This is due to crystal structure. After manganese, iron, cobalt, nickel, the size is almost constant. Then after nickel, the size increases. Take two. Now, here, like to do this point. Observe, student, observe carefully. So if you plot, for example, size or atomic radius, right, in y-axis, and atomic number in x-axis, right, atomic number, right. How size varies in the case of 3D series. For 3D series, students observe carefully, size decreases from scandium to chromium, size decreases. After chromium, okay, for manganese there is a slight increase in size. Then after manganese, the size, this is for manganese, then the size for iron, cobalt, nickel, copper, right, up to nickel the size is almost constant. After nickel the size increases, okay, for copper and zinc. This is for copper and this one is zinc. Okay, so I have shown in a graphical manner. Keep this point in mind, very very important, student. Why size decreases from scandium to chromium? Scandium to chromium size decreases. Can you tell me the reason, student? Scandium to chromium size decreases. Why? You just give this answer, very simple. Effective nuclear charge is more compared to shielding constant, compared to screening effect. Okay, if effective nuclear charge is more, size will reduce. Simple. Okay, then second question, why manganese size is large compared to nearby elements, compared to say chromium, and this side we have iron, compared to chromium and iron. What's the reason, student? Can you tell me the reason? Why manganese size is large compared to chromium and iron? What is the reason? Due to the typical metallic structure or typical crystal structure of the manganese. Take down. Due to typical crystal structure of the due to typical crystal structure of the manganese. You just give this answer, is sufficient. Then third point, after nickel size increases. What's the reason? Right, from nickel to zinc, what happened to the size? Size increases. Why? Students, what's the reason, student? Can you tell me the reason?
Shielding energy is less. So
Yeah, shielding effect. Don't say energy, it is shielding effect. I'm very sorry. Effective nuclear charge and screening effect. If you compare, screening effect is more compared to effective nuclear charge for these elements. Therefore, size increases. Is this clear? Okay, these 3 points are very important for 3D series. Note down. Okay, student. Now, any doubt? Any doubt up to this? Students,
no,
any
sir.
doubt? Yeah, good. Now see this one. This is very important. How size of 3D, 4D and 5D series element vary? 3D series is present at the 4th period. 5D series belong to 5th period. 4D series. 5D series belong to 6th period. When you move down the group, student, in general, when you move down the group, size increases. So what is expected? The expected is that when you move down the group, size increases. So compared to 3D, 4D size is large. Compared to 4D, 5D size is large. Okay, this is what we expect. But in actual practice or in experiment, what is observed in experiment is that compared to 3D series, 4D series elements have larger size, no doubt. This is correct. This is correct. But if you compare 4D series and 5D series, elements of 4D and 5D, if you compare, their size is almost equal. Size is almost equal. What is the reason? Why? Why 4D and 5D series, right, have almost equal size. What's the reason? The reason is that, students, when you move from 4D to 5D, one second, let me take the elements. Yeah, see here, student. These are the element present in 3D series, 4D series, 5D series. Okay. After lanthanum, students, after lanthanum, we have 14 elements. Okay, which are actually in the periodic table. Then after lanthanum, cerium supposed to come. Cerium, right? Cerium, then it goes up to lutetium. Here we have totally 14 elements. Students, observe carefully. But these 14 elements, they are supposed to come here in between lanthanum and hafnium, but they have some peculiar properties, special properties. They show similar properties, okay, which are not the usual property of D block element. So these elements are separated in the from the periodic table and kept at the bottom as F block. This is called lanthanide series. Cerium to lutetium, this series of elements are called lanthanide series. In lanthanide series, there is an effect, famous effect, which is present, actually called lanthanide contraction. There is a contraction called lanthanide contraction, which is very, very important. There's a lanthanide contraction. So when you move from cerium to lutetium, size decreases uniformly. There is a uniform decrease in size. So that's why lanthanide contraction is very special. Because of that, students, because of that, when you move down the series from 3D to 4D, 4D to 5D, size supposed to increase. But due to lanthanide contraction, if you compare the size of zirconium and hafnium, okay, here there is no lanthanide contraction because there is no lanthanide elements here. But between lanthanum and hafnium, lanthanide contraction is there. Because of that, the size of hafnium is not increasing in larger extent. Due to the contraction, the hafnium size is little bit small. So zirconium and hafnium, they have comparable size. Similarly, niobium and tantalum, similarly molybdenum, tungsten, they have comparable size. What is the reason? The reason is lanthanide contraction. So why 4D series and 5D series elements have almost equal size? It is due to lanthanide contraction. Lanthanide contraction. Take them, student. Due to lanthanide contraction. Is this clear? Sometimes they ask, zirconium and hafnium have almost the same size. Almost same size. What's the reason? What's the reason? Very simple. The reason is lanthanide contraction. Is this clear, student? Students, is this point clear? Hello?
Yes, sir.
Yes, take down. Due to lanthanide contraction, zirconium and hafnium have almost the same size. Okay. So, if you plot the size of 4D series and 5D series here, this is 3D. Okay, these are the 3D series elements. Now I'll plot the 4D series. 4D series elements vary like this, and if you see 5D series element, this is 4D. 5D series elements, they have size close to the 4D. They have size close to the 4D. The size of 4D and 5D elements are very close. Compared to 3D series, these are all elements of 3D series. Compared to 3D series, 4D series elements have larger size. But 4D and 5D, they are very close. It is because of lanthanide contraction. Okay, student, take two. But this is an important question here. If you compare scandium, which is present in 3D series, scandium, okay, then yttrium 4D series, then lanthanum 5D series. Students, observe carefully. Group number 3, the elements of group number 3 is scandium, yttrium, lanthanum. If we go down, actually what we expect is scandium to yttrium size should increase. Then yttrium and lanthanum supposed to have equal size, But what is observed is that scandium to yttrium size increases, no doubt. Yttrium to lanthanum, size of lanthanum is larger. Why? What is the reason? They ask this question. Between yttrium and lanthanum, there is no lanthanide contraction, student. Here, no lanthanide contraction. No lanthanide contraction, so size increases as expected. Okay, lanthanide contraction is observed. Lanthanide contraction is observed between these elements. After, that is, it starts to observe from group 4 onwards. Lanthanide contraction effect is observed in D block from group 4 onwards, not in group 3. Because, point clear? Lanthanide contraction effect is not observed in the D block elements belong to group number 3. It is observed only from group number 4 onwards. Okay, the size of zirconium and hafnium are almost same. Niobium and tantalum are almost same. It is because of lanthanide contraction. Whereas yttrium and lanthanum size are not equal. The size of yttrium, and if you compare lanthanum size is large. Okay, lanthanum size is large. It is because there is no lanthanide contraction here. Here we get the expected one. As we move down the group, size increases. Okay, is this clear? So we have discussed about 3D, 4D and 5D, how the size varies. Now we'll take the size of the ions. How size of ion varies. Okay, ionic radii. I'm going to consider only 3D series. So in 3D series, I'm going to take metal in the +2 oxidation state: scandium, titanium, okay, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc, all elements in their +2 state. How size varies. Students, in the case of ions, as we move from left to right, okay, size decreases. Right, from left to right. Size of the ion decreases. That is, ionic radius decreases. Okay, take down. This is what usually observed. When you move from left to right, nuclear charge increases, effective nuclear charge increases, size increases. Why? The reason is effective nuclear charge increases. Size decreases. Why? Because effective nuclear charge increases. Take down. This is usually observed, or what we expect normally. Is this clear, student? Any doubt?
Yes, sir.
Yes, good. Take down. Students. Now, let me go to the next important property. So we have completed size. Okay, now I'm going to consider the next important property, that is melting point. Melting point of these elements. Melting point. Student, what is melting point? It is the temperature at which a solid. So you have metal in the solid state. On heating, the metal will melt and become liquid, correct? The temperature at which the melting starts, is called melting point. I can say simply like this. Okay. Now listen student, how the melting point vary from left to right, okay, in D block. How the melting point vary. Listen student, some metal melts at low temperature itself. Some metal melts only at high temperature. What is the reason behind the melting point? Why some metals have high melting point? Listen student, solid metal become liquid. When the conversion takes place, what will happen? The attraction between atoms, metal atoms in the solid decreases. So in solid, one metal atom and another metal atom are attracted by a bonding called metallic bonding. If the metal atom has strong metallic bonding in the solid state, then the melting point will be very high. So melting point, I'll just put MPT, melting point, is directly proportional to, students observe carefully, is directly proportional to the metallic bonding, strength of metallic bonding. Strength of metallic bonding. And another important point student here, metallic bonding, strength of metallic bonding depends on number of unpaired electrons present. Okay, so strength of metallic bonding, let me write here, strength of metallic bonding, okay, this is directly proportional to number of unpaired electrons present. Number of unpaired electrons present in the atom, because when we have unpaired electron, then there is a chance to form metal bonding, metal bonding. So metal bonding become very strong as the number of unpaired electron increases, in general we say. Okay, now let me take the 3D series. I'll show you how this varies. I'll take 3D series student. Mostly for your level they'll ask questions from 3D series. So in 3D series we have elements like scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper and zinc. These elements are belong to 3D series. Clear? Now students observe carefully. Scandium electronic configuration, you know, 3d1 4s2, 3d1 4s2, 3d1 4s2. Here we have paired electrons, so don't worry about that. But in D subshell we have one unpaired. So scandium has one unpaired electron. I'll write here. It has one unpaired electron. If you go to titanium, the electronic configuration 3d2 4s2, the 2 electron present in S subshell is paired, whereas the 2 electron present in D subshell is unpaired. So here we have 2 unpaired electron. In vanadium we have 3 unpaired electron, because the electronic configuration is 3d3 4s2. In chromium, you know the configuration 3d5 4s1. Students observe carefully. In S subshell we have 1 unpaired electron. In D subshell we have 5 unpaired electron. So there are totally 6 unpaired electrons are there. So chromium has more number of unpaired electrons. In the case of manganese, the electronic configuration is 3d5 4s2. So S subshell is paired. So we have only unpaired in D subshell and we have 5 unpaired electrons in manganese. Then iron 3d6 4s2. Listen, 4s2 is fully filled. In D6, you know very well, if you arrange the electrons in D subshell, we have 6 electron now, so put 1 1 first, 1 2 3 4 5, then 6th electron is paired here. So how many unpaired electrons? We have only 4. So iron atom has 4 unpaired electron. Similarly cobalt 3d7 4s2, okay, it has 3 unpaired electron. Nickel 3d8 4s2, it has 2 unpaired electron. Copper 3d10 4s1, students observe carefully, 3d10 4s1, it has only 1 unpaired electron, and there is no unpaired electron in zinc. Zinc 3d10 4s2, no unpaired electron, 0. Okay, That is the reason why, since there is no unpaired electron in zinc, listen student, metallic bonding in zinc is very, very poor. So we can say that these atoms are soft metals. Listen student, soft metals. Soft metal means they melt readily. Right? In 3D series, zinc is called as soft metal. In 4D series, cadmium is called as soft metal. In 5D series, mercury is called a soft metal. Listen, mercury is very, very soft, so it exists as a liquid. Correct? Mercury is a liquid metal. What's the reason? It is very, very soft. Okay, the metallic bonding is so weak. Soft metal means, what is the meaning for soft metal? Soft metal means very weak metallic bonding. Very weak metallic bonding. Because there is no unpaired electron. Very weak metallic bonding. So they are called as soft metals. Soft metals means they have very low melting point, student. Very, very low melting point. Zinc, cadmium, mercury, they readily melt. And you know very well, mercury melting point is below room temperature. Below room temperature, below 30 degree. So that's why mercury exists as a liquid, right? In our condition. Clear? Now students observe carefully. So when you move from left to right, number of unpaired electron increases up to chromium. Correct? Therefore, if I plot, I'll show in this manner so that you can easily understand. Melting point versus atomic number. Atomic number I plot. For 3D series, listen student, from scandium to chromium, melting point increases. Chromium has the highest melting point because it has maximum number of unpaired electron, so metallic bonding is very strong. After that, for manganese, there is a large decrease. For manganese, there is a large decrease. It is due to the crystal structure. It has unpaired electron, 5 unpaired electron, but the crystal structure, okay, in which the metal atom is somewhat larger in distance. The distance between metal atom is large. So metallic bonding, even though it has 5 unpaired electron, the metallic bonding is not that effective. After that, we have iron, then cobalt, then nickel, then copper and zinc. It goes like that. Okay, so this is for manganese, this is iron, cobalt, nickel, copper. Zinc has very low melting point, lowest among all D block. So this is scandium. From scandium to chromium, melting point increases, and melting point is highest for chromium in 3D series, student. Take down. Which element has the highest melting point in 3D series? Chromium. Why? Because it has maximum number of unpaired electron. When we have more unpaired electron, metallic bonding will be very, very strong. Okay, take down. Clear, student? Clear? Any doubt? This is 3D series. 3D. Similarly, in 4D series, molybdenum has, okay, just I'll show you here. Molybdenum has the highest melting point because it has maximum number of unpaired electron. Then this is 4D. In 5D series, tungsten has the highest melting point. Tungsten. You know very well, in the entire periodic table, the element tungsten has the highest melting point. That is the reason why we are using tungsten in electric bulb filaments. Okay, in electric bulb, no. In bulb, we use tungsten as a filament. Why? Because tungsten has high melting point. So even if you go to very high temperature, it will not melt. Okay, take this one. What is the reason? The reason is strong metallic bonding. This is very important discussion, student. Keep this in mind. Very useful for your competitive examination also. Clear? Students?
Yes, sir.
Yeah, good. Now, now let me ask few questions, then we'll move further. Questions. Students, tell me, in 3D series, chromium has maximum melting point or highest melting point. Highest melting point. Okay, why? Yes, can you tell me? In 3D series, chromium has the... Yes?
Strong metallic bonding.
Very good, ma'am. Good. Very good. Yes. Chromium electronic configuration 3d54s1. It has 6 unpaired electrons. Unpaired electrons. Therefore, metallic bonding is very strong. It has strong metallic bonding. Okay. Therefore, has high melting point or highest melting point. Melting point in 3D series. Clear, student? Like this you have to answer. Chromium electronic configuration 3d54s1, it has 6 unpaired electron. Because of that, metallic bonding is strong. Clear? Is this clear, student? The second question is, in 3D series, manganese has melting point lower than iron. Yes, give reason why. Manganese has melting point lower than iron. Why? Student, what is the reason?
Sir, it is
Metallic
an
bonding.
exception metal, sir.
Very good. Good, ma. Good. The answer is this. Manganese has 5 unpaired electrons. But metal distance, right? Metal distance in crystal is large. So even though there are 5 unpaired electrons, okay, metallic bonding is not effective. Metallic bonding is not high as expected. It's not high as expected. Clear, student? Is this clear? It has 5 unpaired electrons, no doubt, but metal distance in the crystal structure is large. Because of that reason, metallic bonding is not high as expected. Therefore, manganese has lower melting point compared to iron.